I'm Diederik Vink. I'm originally from the Netherlands. I'm a PhD student at the Circuits and System Group at Imperial College. I've spent my undergrad years here learning all about electrical engineering, which essentially led me to find my interest in accelerating machine learning through hardware acceleration, which I was able to explore in depth here at Imperial. The custom hardware accelerator that we built is based on the principle that if you have a specific workload or problem, a custom solution is always the best way to go about it. Using this inspiration, we use something called field programmable gate arrays, or FPGAs for short, which is a type of configurable hardware. Using this configurable hardware, we built an accelerator that can adapt to any kind of incoming workload. So we focused on convolutions. There's a large range of sizes and dimensions for the convolutions you see during CNN training. The CNNs, also known as convolutional neural networks, are a popular form of machine learning. They're used in a wide variety of applications, from self-driving vehicles all the way up to helping identify diseases within radiology. The big limitation that we have with CNNs nowadays is that they take incredibly long to train, and therefore there is quite a large push and quite a large need to be able to make this training more efficient and more accessible to users that aren't just large corporations, but that have simpler setups like in research labs or users at home. We've made a system that can adapt to each one of these convolutions to most efficiently execute that convolution, which allows us to overall efficiently and quickly train CNN. The algorithmic approach we took to accelerate training focuses on quantization. The idea here is if you use less bits, you're able to perform the same operations faster and more efficiently. But this introduces something called quantization error, which can affect the final accuracy of the network that you train. So what we did is we built a feedback system that measures how far we're deviating with training, how big this error is, and if the error is too big, we increase the number of bits that are used. It might decrease performance, but it increases the accuracy. Overall, this allows you to train faster, more efficiently, but to still have the same final high accuracy result at the end of training. The real-life application that I personally find the most interesting is related to space and specifically satellites. If you have CNNs training on a satellite, if you want to change what it's training or if you want to change what is operationally happening, you'd have to bring the satellite down, reconfigure and update everything and send it back up. This is time-consuming and very expensive. What would be easier is if you had an FPGA up on your satellite, which you can then from Earth reconfigure to perform whatever actions you needed. So if you have a satellite that's training while it's in space to, for example, track logistics or do object detection with the camera that it has, if you could reconfigure that process from Earth whenever you wanted to change it, our ecosystem would be the optimal way to do that.